A conformal map is a function that locally preserves angles and the sense, clockwise or counterclockwise, of those angles. Imagine drawing a tiny grid on a rubber sheet. When you stretch the sheet with a conformal map, the little squares become tiny rhombi that keep the same corner angles. In complex analysis, a map f of z equals u of x, y plus iv of x, y is conformal at a point z0 if it is complex differentiable there, and its derivative f prime of z not equal to 0. The condition for complex differentiability is given by the Cauchy-Raman equations. U sub x equals v sub y, u sub y equals negative v sub x. If these two partial derivative equalities hold in a neighborhood and the partials are continuous, then f is analytic, holomorphic, and thus conformal wherever f prime of z not equal to 0. The requirement f prime of z not equal to 0 guarantees that the map does not collapse the infinitesimal neighborhood to a point, which would destroy angles. Linear or affine conformal maps have the simple form f of z equals a z plus b, where a and b are complex constants, and a not equals 0. The factor a does two things at once. Its magnitude absolute a stretches or shrinks distances uniformly, a scale, while its argument a rotates every figure through the same angle. The added constant b translates everything without changing shape. For example, rotation, a equals e to the I theta, absolute a equals 1, turns the whole plane by theta radians, just like turning a map on a table. Uniform scaling, a equals r greater than 0, real enlarges or shrinks everything like zooming a camera. Translation, b moves the origin to a new point, analogous to sliding a sheet of paper without rotating it. Because the derivative f prime of z equals a is constant and never 0, these maps are conformal everywhere. Tiny angles are exactly preserved. In engineering, these maps are used to align coordinate systems. For example, converting a sensor's local coordinates to a global frame by rotating and shifting the data. A Möbius fractional linear transformation is any function of the form f of z equals open parenthesis, a z plus b close parenthesis, divided by open parenthesis c z plus d close parenthesis. With complex numbers a b, c, d satisfying a d minus b c not equal to 0. Such maps are built from a sequence of simple steps: translation, scaling or rotation, inversion, z goes to 1 over z, and another translation. Because each step is conformal except at points where the denominator vanishes, the whole transformation is conformal on its domain. A striking geometric property is that circles and straight lines are mapped to circles or straight lines. The image of a line can be a line or a circle, and the image of a circle that passes through the pole, the point where cz plus d equals 0, becomes a line. Real-world analogy, think of a flexible but unstretchable wire frame, a circle. If you pull the frame through a hole, the inversion step, and then rotate it, the shape may become an oval or a straight line, but it will never turn into a jagged polygon. Möbius maps are heavily used in fluid dynamics, potential flow around objects, and in electrical engineering to transform impedance circles on the Smith chart. Two of the most useful domains in complex analysis are the unit disk d equals the set of z such that absolute value of z is less than 1 in the upper half plane h, equals the set of z such that the imaginary part of z is greater than 0. The Cayley transform connects them, w equals z minus I divided by z plus I. If z belongs to h, the denominator never vanishes and the image w satisfies absolute w less than 1, that is, w lies inside the unit disk. The inverse map is z equals I times 1 plus w divided by 1 minus w, which takes any w in the unit disk back to h. Geometrically, the transform bends the infinite half-plane so that its straight boundary, the real axis, becomes the unit circle while preserving angles. Engineers use this to convert problems defined on a semi-infinite region, like a semi-infinite strip of material, into a bounded region where numerical methods converge faster. Power, exponential, and logarithmic functions are basic building blocks for more complex mappings. Power map f of z equals z to the n integer. In polar form, z equals r e to the I theta. We have f of z equals r to the n e to the I n theta. The radius is raised to the nth power, stretching or shrinking radially, and the angle is multiplied by n, rotating n times around the origin. For n greater than 1, the map folds the plane n to 1, so each angle in the image corresponds to n different angles in the source. Exponential map f of z equals e to the z. Write z equals x plus iy. Then e to the z equals e to the x times open parentheses cosine y plus I sine y close parentheses. The real part x becomes a scaling factor, radius e to the x, while the imaginary part y becomes the angle. Horizontal strips of width 2 pi in the y direction map to the same annulus, showing the periodicity of the exponential. Logarithm, the inverse of the exponential, f of z equals log z equals ln absolute value of z plus I argument of z. Because the angle is multi-valued, adding 2 pi gives the same point. We cut the plane along a ray, commonly the negative real axis, to define a single branch. The branch cut is like a seam in a piece of cloth. You cannot cross it without jumping to a different sheet of the function. These considerations are crucial when designing conformal grids for heat transfer problems, where one wants to avoid crossing a branch cut that would flip the temperature field. The Joukowsky transformation is defined by W equals 1/2 times the quantity z plus 1 over z. It is a special Möbius map that combines inversion, z goes to 1 over z, with averaging. For points on a circle, absolute value of z equals r. With r not equal to 1, the image is another closed curve. If the original circle does not pass through the origin, the map turns it into an airfoil-like shape. The front part becomes a rounded leading edge, while the back edge becomes a sharp trailing edge. When the circle is the unit circle, r equals 1, the denominator 1 over z equals the complex conjugate of z on the circle, and the transformation reduces to w equals the real part of z. That is, every point on the unit circle maps to the line segment -1 to 1 on the real axis. This property is used in aerospace engineering. By choosing the radius and center of the original circle appropriately, one can generate the classic Joukowsky airfoil, then apply potential flow theory, which is conformal, to compute lift and pressure distribution. Explanation: the Schwarz-Christoffel (SC) formula gives an explicit way to map the upper half plane H onto the interior of a polygon with vertices W sub 1 through W sub n. If the preimage points on the real axis are x sub 1 less than x sub 2 less than x sub n, and the interior angle at vertex W sub k is alpha sub k in radians, the map is f of z equals c plus a times the integral from z naught to z of the product from k equals 1 to n of open parenthesis, zeta minus x sub k close parenthesis, raised to the power alpha sub k over pi minus 1 d zeta. A and c are complex constants that adjust scaling and translation. The exponents alpha sub k over pi minus 1 are negative when the angle is less than pi, causing a turn in the image. Example rectangle. A rectangle has 4 right angles, each alpha sub k equals pi over 2, so each exponent becomes negative 1/2. Choosing the preimage points x sub 1 equals -1, x sub 2 equals 0, x sub 3 equals 1, x sub 4 equals infinity, the integral simplifies to f of z equals c plus a times the integral from 0 to z of d zeta divided by the square root of open parenthesis zeta plus 1 close parenthesis times zeta times open parenthesis 1 minus zeta close parenthesis. Evaluating this, often with elliptic integrals, yields a map that sends the upper half plane to a rectangle. In engineering, this is used to convert a complex cross-section, for example a channel with right-angled bends, into a simple rectangle where analytical solutions of Laplace's equation are known. Prove conformality. Let f of z equals e to the z show that f satisfies the Cauchy-Riemann equations everywhere and that f prime of z equals e to the z not equal to 0, therefore f is conformal on the whole complex plane. Hint: write z equals x plus iy in separate real and imaginary parts. Determine the image of a region. Use the Möbius transformation W equals open parenthesis z minus 1 close parenthesis over open parenthesis z plus 1 close parenthesis to find the image of the right half plane, real part of z greater than 0. Show that the boundary line real part of z equals 0 is mapped onto the unit circle, absolute W equals 1, and conclude that the whole half plane maps onto the interior of that circle. Apply Schwarz-Christoffel to a rectangle. Map the upper half plane onto a rectangle of width A and height B. Choose preimages x sub 1 equals -1, x sub 2 equals 0, x sub 3 equals 1 on the real axis and set the interior angles to pi over 2. Write down the Schwarz-Christoffel integral, evaluate it. You may quote the standard result that the integral equals a times k of k and b times k prime of k, where k is the complete elliptic integral. And solve for the scaling constant a so that the rectangle has the prescribed dimensions a and b. These problems require students to combine analytical calculations with geometric insight, mirroring real-world tasks such as designing conformal meshes for finite element simulations.